You guys. Second here.
Are you excited to go back to school, Mr. A?
I am actually, yeah, I am. Are you?
I am. I've been wanting to go back since January 4th. And then whenever they said it got moved back to March, I was like, that sucks. But
I think it's been the right thing to do. I mean, things are getting better now, I think, and it's hard to know. I know that, this is hard for you guys and me, and little kids are the worst, though. I mean, my buddy's got a first grader, and I mean, for a little, I think, one thing that would make sense is to kind of, do the little kids earlier than the high school kids. I think, the experience seems to indicate that, small kids are not transmitting the virus as much. So, and they're probably hurt the worst, with, not being in school. And, I've said before that, the high school students are going to be like the worst behaved out of fear. Maybe not, but, and, you guys are the ones that could probably deal with it the best. But I don't know, I'm ready to be back. Okay, we got a couple more here.
Will say the timing's a bit unfortunate. I just realized I could put my laptop on the corner of my L desk, and now I have 2 workspaces, and it's much greater space optimization. And I just realized that a few days ago. And so, the moment that we're no longer going to be working from my desk every day, I find that great trick.
Life's tough, and it gets harder. So, if that's your biggest problem right now, then I guess, you're fortunate. I am hoping that this big freeze, it's kind of like Mother Nature's, lockdown. It might really help some of the numbers just because people are too cold to, go anywhere. But we'll see. So today I want to talk about the finding the length of a curve. And what I mean by that is, say you take like a parabola or something and you grab the ends and you just stretch it out into a straight line and measure it. That's kind of, what I'm talking about here. So let me switch over, and so there's a formula. I'll write it down. Ultimately, this is like a multiple choice question on the BC test, maybe like a part B or C of a for response, but I kind of doubt that. It's more of a multiple choice type question. Ultimately, you use the formula, you do it, you go on, you get an answer. But I do want to derive the formula for you so you have some context also. Okay, well, you may help Ben out when later on. Thanks for telling me. This is kind of bright. Let me turn the lights down a little bit. Right back. Okay. So length of curve. There's your formula. take the derivative of the function, square it, 1 plus that, square root, integrate the whole thing. So like I said, when you're taking the AP test, that's what you do. And it'll likely be a calculated question because it's unlikely that this is going to come out to be a nice integral to go forward with. So unless it was like maybe an arctan one, but still, I would expect this to be a calculated question. So anyway, that's nice. Let's draw a picture. I always like to have a parabola, but let me see if I have a different color. Try this. Okay, so here's my just a parabola. Look at A to B. What I'm talking about is grabbing these 2 points, stretching, pulling hard, stretching them out straight, and then seeing how long that is. So what I want to do first is I want to just pretend that we have a straight line here. Like that, because that straight line, I do have a good way to find the length of that straight line, the Pythagorean theorem, but I don't really have a specific formula for this particular shape. So the issue you kind of run into here is not having there's lots of different various shapes you could have. You could have a cubic or whatever. And if you don't have a nice formula, you have to kind of, the theme of calculus is cutting up something that's not workable into little tiny pieces that are workable, and then kind of using like estimates of each of those little pieces to form your what it is you really want. This straight line is not the same length, but it's kind of somewhat close. And I could also draw a little right triangle here. If I know this height and this width, I could draw a little right triangle, find the length of that line. Anybody want to take a shot on whether this is an under guess or an over guess?
Under guess.
Under.
Yeah, it's under guess. If you walk directly from here to there, that's shorter than if you walk kind of meandering from the same start to the same end. So yeah, definitely an under guess. And probably a pretty substantial under guess because a straight line and a curved line just aren't quite the same thing. So what I'm going to do is I'm going to get rid of that. And I'm going to just draw a bunch of intermediate points. Maybe we'll just start with 2 intervals. Maybe that would be better. So maybe pick a midpoint here and do that line right there, and that line right there. So if I pick that point, I've got that hypotenuse, and I've got a second hypotenuse. And if I add those together, then I still will end up with an estimate. This straight line looks kind of like that curved line. More so it looks like it. This straight line more so kind of looks like that. And what you'll end up noticing is that the more pieces you pick, maybe just humor me one more time. The more pieces that you pick, the better your estimate gets. Like say we did 4 of these. So say you do that one, and then we do that one, and then that one. So you can see with even just 4 intervals, suddenly my little short linear segments look pretty darn close to my segments that are, while still curved, locally, look pretty linear in each of those little snippets. So hopefully you can already be a couple steps ahead of me here and say, okay, if I have an infinite number of line segments that are infinitely short and linear, if I take those infinite number of is it hypotenuses or hypoteni? I don't really know what the plural of hypotenuse is, but we'll just, pretend like I do. Add them all up, and that will be eventually an exact length for whatever your curve might be. So looking at the formula again, I'm going to just erase this one more time and go back to we'll just go back to 2 because that makes it a little easier for me to see. There's 1, there's 2. So if you look at one of these, it just looks really sloppy too. I'm going to draw this over on the side also so you can kind of see the blown up version. So this is my unknown. I want that question mark. This width, that is dx. And then the height is dy. It's unknown because if I'm dealing with an infinite number of segments, I do need a uniform width. That's something that's required. We've had that all year when we talked about the definition of an integral, and I had like the uniform width. In order to kind of do this in an automated way, we need the width to always be the same. So the width for every one of these, spaces is, whatever halfway is from A to B here if I have 2, but dx for this and then dy up there. And so now I'm going to have this as the square root of dx squared plus dy squared. So that is what I want to add up. And let's just kind of go back here. So this is the length of one L sub I. L sub I is the square root of dx squared plus dy squared, just like that. How are we doing so far?
Makes sense.
L sub I, when you see a sub I, that's like the index number. And 1, 2, 3, 4 of the represent the different, triangles. So here we'd have L1 and L2 if I'm just doing 2. So anyway, I want to add those up. But first I want to kind of change the format a little bit into something that's easier for me to work with. So, I always prefer to have derivatives instead of differentials. And so if I'm going to multiply this by 1. And what that's going to look like is going to be this. Actually, before let me make this a little bit bigger. Before I multiply, anybody want to kind of jump in and make a suggestion for what would you like to see happen in this square root? You can cheat and look at the formula too. What?
Get d of y in terms of d of x.
Not in terms, but maybe I'd like to see if I have a dy, I'd like to see it become dy over dx, because that's something that I can deal with. That's something that I can get to really quickly. I know what dy over dx is. That's a derivative. Is that kind of what you're saying?
Yeah.
Okay. So I'd like to multiply this by maybe 1 over dx squared inside. Does that make sense?
Yeah.
Let me write it down and see if that helps. So I want underneath this, I want to have a dx squared under here, because that will match this, and it will be something that I'm familiar with. Also, if I were to multiply this, the bottom by dx squared over dx squared would also become 1. So if I'm able to, if I could get a dx squared under here, and if I could get a dx squared under here, that would give me dy over dx squared. And it would give me dx squared over dx squared, which is 1. Does that objective seem like a, you kind of see where I'm going? To get a dx squared underneath the radical, you're going to have to multiply by that, by the square root of dx squared. Can you see that okay?
Yeah.
And if you want to do that on top, if you want to do that on bottom, you also have to do it on top. And so what you're going to find is you're going to have now the square root of dx squared is not going to go anywhere, but you're going to have dx squared, sorry, over dx squared plus dy squared over dx squared. So anyway, this is where we are. I'm going to notice that this is 1. dy squared over dx squared is really just dy over dx squared. And the square root of dx squared, what's the square root of something squared?
The original.
So that's just dx. And we get an integral there to add up all of them from a to b. And that is your formula up top. So just a quick little kind of derivation and picture to show you, with all these formulas, I do want you to just, remember the formula. That is, always a good plan. But it's always nice to know where it comes from, and, not only to just have kind of a good understanding of what you're doing, but also, if you do forget the formula, that you can just kind of derive it. I'm personally not like a great flashcard person. Some people are. I prefer just to kind of know that if I forget something, I can derive it real quick and be ready to roll. So I think that's kind of the ultimate self-sufficiency plan, which is what what's wrong down here. That's why I like to spend a little time doing this. Let's go ahead and actually utilize the formula and practice it. Before I take this page off, any further or last comments on what we just did? As we were talking about this, I did remember, I told you this is a great multiple choice question, but before the blizzard, when we were doing rotation of solids, I just remembered there was one free response question where they asked you for the length of the curve, and I said we're going to skip this for now and come back to it later because we hadn't learned that yet. So obviously, I'm wrong. There was a part B or something of a free response question that utilized this topic. But anyway, let's just practice a few cases. Yeah. We'll just start with kind of something pretty simple, and then we'll look at some that are not maybe solve y in terms of x like you're used to. But let's just do y equals x squared minus 3x plus 2. This is just a simple quadratic equation, and maybe we'll do x goes from -3 to 2, if you want a quick refresher on how this looks, this would be like x minus 2, x minus 1. So you'd have like barely come down. And I think it would go down to like negative a quarter, like something like that. Anyway, so we're going from like negative 3 up to 2. That we want that length. Notice that this includes not only one side, but the vertex and part of the other side. That doesn't make any difference, but it just makes it look a little different than what I just did a moment ago. So the length, if I set this up, it's going to go from minus 3 to 2. Square root of 1 plus the derivative squared. The derivative is 2x minus 3. And like I said, with most of these, you're going to utilize the calculator because, it's probably not going to be an easy one to work out yourself. So while we're here, if you did want to do this by hand, let me just kind of tell you like what you would want to think about. I'd multiply all this out. I do completing the square to try and get this set into 2 squares, and then I'd try and make it look like one of the arc trig functions, kind of format it so that it looks like if I could do like something squared minus something squared in terms of x, maybe an arc cosine or something, but we're not going to do that. That's not the objective for today or ever. Just saying. So math, and we'll go down to function integrate, and we're doing this from, what did I say, negative 3 to 2. And then we'll do the square root of 1 plus 2x minus 3 squared. And with respect to x, what am I doing? How about enter instead of graph? I want to say that's, call it an 21 2/3 to kind of keep, roughly 21.67. Let's go to the graph, and I want to just check. I think there's a way to do this on the calculator on the newer ones, but I can't remember. There's your graph. Squared minus 3x plus 2. Did I minus 2 minus 1? Oh, my window's all jacked up. There we go. That looks more like it. Let's go to just second calc real quick. Integral, derivative. No, I guess it doesn't. It won't do that for you on this these newer calculators. I thought it might have, but anyway, that's all there is to it. Any comments on this problem? Okay, let's look at this one. This one's a little bit more interesting. It's not solved in terms of y in terms of x. So you're going to have to solve this for y first. Also, they give you 2 points, one to start, one to end. And the reason they give you actual coordinate points and not just up here x is between minus 3 and 2 is you're going to find that this is not a function. And so that doesn't mean it's bad. It just means that you need to kind of select the correct piece that that you're dealing with. If you do a restricted range where you cut off like the bottom part, maybe this time you need to cut off the top part. That's what this is going to tell you. But let's first solve this for y. To solve this for y, you're going to have to do complete the square, like I was just mentioning in the previous problem. And actually I might just start this on a new piece of paper because I think I'm going to run out of space. So hopefully you remember your algebra 2. And if you take half of that, half of 2y is 1y. So I'm going to just write down half of that. Y was 1. And so I'm going to just write y plus 1 squared. And that is y squared plus 2y plus 1. And looking at that, I'm now wishing that, oh, what if I just had a plus 1 there? And so you're allowed to just slap a plus 1 in there as long as you slap in a 1 on the other side. So you can do plus 1, but also do a plus 1 there. So that's kind of your obligation. If you want y squared plus 2y to factor nicely like it would here, then maybe you just need to slap in a plus 1 so it matches this and thus matches that. And so now you have y plus 1 squared equals 2x plus 2. And you can take a square root and get y plus 1 equals, I'm going to say plus or minus the root of 2x plus 2. And finally, to solve for y, you take away 1, so you have negative 1 plus or minus root 2x plus 2. I'm going to put a box around that. We're just doing algebra 1 so far. I'm going to write down the points again, negative 1 to 7, 3. Before I continue, any hiccups on the algebra part of this? Okay, I just typed in negative 1. Can you guys read that? I'm not sure. Is that better?
I can.
Yeah, it's better.
We're going to graph that and see what we get. Remember, I had plus and minus in the middle, and I'm just doing plus. So let's just see what that looks like in the standard zoom window to begin with. So that's one portion of it. If I graph the other portion, just for giggles, negative 1 minus the square root of 2x plus 2. That's that kind of other side of it. Why? Oh, okay. So now let's think about the point negative 1, and 7, 3. I want to figure out which branch I want by figuring out which one of the branches has those 2 points on it. So if you look at, say, if you go to trace, y1 is the one with the plus, and then y2 is the one with the minus. You can see the cursor. If I do up arrow, it bounces from y1 to y2. So let's type in negative 1, and you'll see that with y1, if you put in negative 1, you do have that point at the far left side of that top curve. And if you switch down to y2 and type in negative 1, you also, that point exists on y2. So negative 1 is part of both curves. So it's going to narrow it down for us is if you type in 7 now, x is 7 into y2, it gives you negative 5. That's not a point that they were discussing. If you go up top, you might have, go to y1 if you put in 7. Now it takes you to 7, 3. So again, the purpose of giving you ordered pairs is to make sure that you can figure out that you want to restrict the range and take the top part, but not the bottom part. Anytime you have something that's a non-function, a circle, there's all these like different loop-de-loop things, like they have weird names, and those are all non-functions. And if you need to say something about those, they're going to, whether it's the length of a curve or what's the tangent line, you need an x and a y coordinate so you can know, if 7, going back to algebra 2, if 7 has an output of 3, but also an output of negative 5, which point are we talking about? The reason, we kind of thumb our nose at non-functions is because, of the lack of specificity where, if x is 7, which one is it? Y, is it 3 or negative 5? Well, if they tell you, then, it doesn't matter if it's not a function. So anyway, I digress a little bit, but I think that's important to mention. Let's go and actually finish this. The the derivative here, obviously -1 is 0. This is like 2x plus 2 to the 1/2, so it's a chain rule. Start like that. That's the outside part of the chain rule. Recopy the inside, multiply by 2, which is the derivative of the inside. So you just get 1 over, that's your actual derivative. And so now you can say length is going to be, now we're differentiating with respect to x, so I just need the x's this time, -1 to 7. And you're going to have 1 plus this derivative squared. And I realize that that does simplify substantially, but I don't think I want to, well, here, just for giggles, I'll just simplify it. 1, if you square a 1 or a square root, you just get 1 plus 1 over, you certainly don't need, if I was taking the AP test, I don't think I'd simplify it because it's just more opportunity to get screwed. But, we will here for right now. And finally, math. Function integrate, we're doing -1 to 7. Square root of 1 plus 1 divided by a square root of 2x plus 2. So 9.7, let's just check that. Let's go back to my picture and just kind of check that real quick. So, and also one other comment, when I took my derivative of this, I made a big deal about choosing whether we wanted the plus or the minus. Okay, we spent a lot of time talking about that, but ultimately the derivative of -1 was 0, and whether this is a plus or minus, I don't think it made any difference at all. It still is important, and you have a non-function to realize that and make sure you pick the right branch, because that is not always true. It's not always true that we have symmetry on my top branch and my bottom branch. Sometimes they might look totally different. So it is important to identify which function you want, but I can see now that, yeah, for sure, these are symmetrical. If I wanted to check 9.7, I can't check it exactly, but I can ballpark check it. That's a, ballpark checking is a really great skill to have, where you say, I got 9.7. Was the answer kind of supposed to be maybe 8 or 10, or was it supposed to be 900? If you can kind of see that at least you're in like the right area, that's in my opinion, a great kind of practical skill to have, to kind of notice that you're, within reason or not at all within reason. So what I'm going to do is I'm going to just draw a little picture with my 2 dots. I'm going to draw that line, that hypotenuse, and then kind of pencil in this and say, well, we went from -1 to 7, that's 8. And then we went from -1 up to 4, that's to 3, that's 4. So this would be the square root of 64 plus 16, which is the square root of 80. And what's the square root of 80? It's about 9. And so this said about 9, that said 9.7. And earlier in the class, we talked about how the curve is always longer than the straight line. So this is an underguess. And does it seem believable that 9 is an underguess of a correct answer of 9.7? I think it probably does. It probably does. Just looking to see if there's any more like remarkable questions. If you have a non-smooth curve, if you have like a, I don't want to be oversimplistic, but say like an absolute value curve where there's like a sharp turn. What you do is you just break that figure into multiple pieces and add the adjacent ones together. I'm just looking at maybe, this curve right here. They say x to the 2/3 plus y to the 2/3 equals 1. So if they said, for example, what's the length of the whole figure? And so what I would do is I would, at most, I would find this piece right here, and just double it, because you'll see this is clearly reflected about the x-axis. I think you'd be pretty safe to find one of them and quadruple it, because these are also reflected over the y-axis. So, nothing weird, just kind of use some common sense sometimes. Yeah, if you try and integrate this from -1 to 1, you're going to have a sharp turn right there. It's not differentiable at 0. So you got to skip that point. So, if you did want to do this, I would solve this for y. You would subtract x to the 2/3, put a 3/2 exponent to solve for y on both sides. Then just integrate it from 0 to 1, and, times 4 is what I would do. So, nothing, like I said, nothing too hard, but then some of these other ones here, let me just go back. Basically, a lot of these are just practicing harder derivatives that are ones you haven't thought about in a while. The derivative of an integral, that's going to be basically tangent when you take the derivative of the integral of tangent from 0 to x. That was the fundamental theorem of calculus. The derivative of secant, tangent. This is a derivative with some exponentials in it. This one you have to do in terms of y, I would recommend. They give you the range in terms of y, so you just do a chain rule there in terms of y, and that's that. This is a product rule right there with a trig function. Nothing too scary. Shouldn't be. How do you guys feel? Should I do a couple more of these, more, or are we, are you? Do you feel good with this, or what should we do for the next few minutes? Maybe I'll just do another one. Here, I'll just do the one I was talking about. X equals the square root of 1 minus y squared. They give you a range. Y goes from -1/2 to 1/2. Just like the formula in terms of x, if you have this in terms of y, it's going to be 1 over dx over dy squared times dy from a to b. Notice, look, I've got dx over dy squared. That's backwards from what you're accustomed to, is because this is the derivative of x with respect to y. The derivative of x with respect to y, it's, obviously going to be flipped. But if you take the derivative of x with respect to y here, it's a chain rule, 1/2. Do that. Recopy 1 minus y squared, multiply by -2y, and the 1/2 and the 2 obviously cancel out, so you get -1 over that. And the length is going to be -1/2 to 1/2, like that. And then we have the square root of 1 plus at least sets it up. I won't finish it there. That's something you can just type into the calculator and finish. But anyway, that's just kind of how it works. I think I'll just stop there. And I've pretty much covers this. As you can see, it's just kind of learn the rule and do it sort of situation. Anyway, look forward to seeing everybody back at school on Thursday. And let me know if there's anything in the meantime I can do for you. Bye-bye.
Bye, Mr. Ray. See you
Hey,
Thursday.
Mr. Abercrombie.
Bye, Mr. Abercrombie.
Goodbye.